Okay, good morning. Let's go ahead and get started. Let's a little bit past 10. All right. So we are continuing our discussion of partition functions. The last time we met, we were talking about vibrational partition functions, and we saw that we could predict, the probability of being in a particular vibrational state. So we've derived the expression for the fraction of molecules in a specific vibration state. And then we also wanted to show that at room temperature, most of our molecules that are diatomics are going to be in the ground vibrational state. So we defined a function that gives us the fraction of molecules in the ground state, and then everybody else, 1 minus that value, corresponds to the excited vibrational state. We did point out that for most diatomic molecules, we're in the ground vibrational state at room temperature. The exceptions are molecules that have weak bonds, and those are associated with very large atoms, so bromine, iodine, and chlorine. Right? From there, we turned our discussion to the rotational partition function. We derived this expression that we've used before. And of course, once we have the partition function, then we can calculate the energy of rotation of the particles that make up our systems. Right? What we saw last time was that most of our molecules are in excited rotational states. We'll build on that a little bit at room temperature. All right, so what we're going to do now is we're going to extend our discussion to polyatomics. So some things that we want to keep in mind. When we've talked about vibrational contributions, we've looked at two extremes. Low temperature, the contribution to the vibrational heat capacity is 0. At high temperatures, that goes to R. And of course, if I'm in between the two, we need to calculate explicitly what the value is. When we've introduced polyatomic molecules and talked about vibrations, we've seen that there are a number of vibrational modes given by 3n minus 5 or 3n minus 6, depending on whether the molecule is linear or nonlinear. And in the case of those molecules, we basically can say each of those vibrational modes can be modeled using the harmonic oscillator approximation. All right? Just another reminder, this vibrational temperature is directly related to the fundamental frequency, and we know that for the harmonic oscillator, the fundamental frequency is related to the force constant or the spring constant. So if I have a stiff spring, that means that it's going to be harder to excite it, right? That in turn means that I'm going to have a higher vibrational frequency and correspondingly a higher vibrational temperature, right? And when I have loose springs, I have the opposite impact. All right. When we talked about nonlinear polyatomic molecules, we said that when we're thinking about rotations, we need to keep in mind that there's 3 moments of inertia, and that's going to impact what we're going to talk about. How many people have seen this expression before? Anybody? No? I don't know. You have? Okay. I don't know why this doesn't show up in your math classes. So when you have a series, you guys are used to seeing that capital sigma or whatever that is for the sum, right? Well, this is a series that we have a product, x1 times x2 times x3. So we summarize that by using a capital pi, and that just means that I'm multiplying through by this index. So it's x1 times x2 times x3. Does that make sense? Okay. All right, so as I said, we're going to be talking about polyatomics. So we need to introduce expressions for rotation and vibrational partition functions, and then we can look at the average energies for polyatomics and the heat capacities, right? And then if we have time, we'll get to partial differentiation today. Okay. All right, and I think what I'm going to do today is we're going to start you guys with a group quiz. Woohoo, this is exciting. All right, so last time we met, we pointed out that for our molecules, we expect that they're going to be in excited rotational states. And we've introduced this equation that allows us to calculate the most probable value of J. I'm going to join those guys. Okay. All right, so just do the first question. All right, and then in this case for today's quizzes, we're going to be letting you do them, and then the answers will show up, right? All right, so last time we met, we pointed out that if I wanted to know the most probable value of j, I would take the function of j, take the derivative of it, set it equal to 0. That's basically what we said here. And as you will find on the homework assignment, that you can go from this equation to that equation by solving for j most probable. This is an approximation, and it's approximation because we expect our value of j to be integral. So whatever you calculate here should be changed to an integral, rounded to the nearest integral. All right? I'm going to give you guys 1 minute to solve the problem, and then we're going to move forward. All right, how many people are done with the first question? All right, 20 seconds. All right, let's go ahead and move forward. All right, so moving into section 6, we need to talk a little bit more about these rotational partition functions, right? So when we've derived the expression for the rotational partition function, it turns out that what we've done is explicitly for heteronuclear diatomics. So for my two atoms, they need to be different than each other. All right? And that's because in this particular case, I don't have some symmetry that's available whenever I have homonuclear atom or molecules. So if I look at A2, that's the molecule, right? I'm going to label one of them, right? And what we know is that I could flip this, and it looks exactly the same, okay? So that's A. Okay, so this gives rise to what we call a symmetry number, all right? So I need to define what that symmetry number is. So that's given the symbol sigma. And this basically is the number of equivalent rotational positions of the molecule. All right. So in this case, I can take A prime, flip it. That looks exactly the same. They're equivalent. That means I have 2 for my symmetry number. In this case, if I flip it, I become YX, and that's not the same as XY, right? So my symmetry number there is equal to 1. Okay? So symmetry equals 1, symmetry equals 2. Okay? All right, and then if you look in the textbook, they look at the example for ammonia, NH3. All right? So NH3 is a non-planar right? So this is a trigonal pyramidal structure. And each of these angles, if you were looking down on it, you could flip it by 120 degrees, and you'd have an equivalent arrangement. So I can put 1, 2, and 3 on here. We agree? Right? So in that case, what do you expect the symmetry number to be? That's going to be 3. Okay? All right, what I'd like you to do in your small team is to do the same thing for BH3, boron trihydride. Now there's a difference between BH3 and ammonia, right? BH3 is a planar molecule, right? Does that make sense? So that's going to impact it, okay? So you guys work on that for a minute, and then we're going to move forward. And again, the answer will show up on the annotated lecture notes today. All right, I've put one hint on the board. That's all I will do, though. Oh, and I didn't change it, did I? That was a bad hint. All right, time is up. Please put their answers down. I'm going to come around and collect them. You guys done? Thank you. Thanks. Thank you. Hey. What's up, Melissa? Thank you. Thanks. Let's see. Do I have yours? I have yours. I got everybody's? All right. Okay, so I will tell you, to not leave you in suspense, that the answer is 6. Okay? All right, but that'll be worked out in detail on the annotated lecture notes. Okay, so let's move forward again. So if you guys could keep it down, it would be appreciated. All right, so at this point, I'm going to do sort of a big global summary. So the molecular partition function for a diatomic molecule with our harmonic oscillator and the rigid rotor, we know the particle partition function is the product of the partition function for translation. So we've previously derived that. Now we have the rotational partition function. That shows up here. This is specifically for linear molecules. And the vibrational is going to be there, and then my electronic, all right? And what we know that we can do with that is then we can take it and determine the energy. So I want to take a moment. I'm just going to highlight. So we have t to the 3 halves. We have t. We have this term with t, and t shows up in here. Because we know that we're going to take the derivative of the natural log of this function with respect to t, that means that we want to be able to separate those out, right? So that's going to be t to the 3 halves, t, well, actually it's just times t, so we'll do that, times t. The next one will be our vibrational contributions, minus theta vib over 2t, divided by 1 minus e to the minus theta vib over t, and then times, this is our electronic contribution, dE over kBt. Right? And then that whole thing gets multiplied by a function that has no temperature in it. Okay? All right, so that basically says I can separate these all out. I can, apply this to the relationship between our particle partition function and our system partition function. We can take kBt squared times the partial of the natural log of that with respect to t. When I do that, the n comes out front, right? Natural log of this, n natural log, so that gives me this term. And then I have the denominator, but we know that's not a function of t. So when I take the derivative of that, we can now say that that's going to go to 0. And we're left with n kb t squared partial ln q with respect to t, holding the volume constant. All right? Okay, so I come back up here and I look at this and I say, well, I'm going to take the natural log of this, and it's this times this, divided by this times that. So I can separate that out into terms. So my first portion of it, the temperature shows up as 3/2 ln t. We know that's going to be translational. The next term, this t, ln t, everything else gets with the function of no temperature. That's going to be the rotational contribution. This is our 0 vibrational point. And then this is the energy above the vibrational point. And then here's our electronic contribution. And then everybody else is summed up in the terms without temperature. So I can take the derivative, the natural log of that, and I end up with this overall equation. We've done this multiple times, so I'm going to go through it pretty quickly. So this is the result. This first term, 3/2 RT, that's our translational energy. That's going to be the same for an atom, for a diatomic molecule, for a polyatomic molecule, right? And if you step back and think about how many translational modes you have, or degrees of freedom, there's 3 of them. So 1/2 RT is associated with each of those degrees of freedom, x, y, and z direction. RT is the rotational energy, and for a linear molecule, we've said we have 2 rotational degrees of freedom. So 1/2 RT comes from each of the rotational degrees of freedom. Again, let's just remind ourselves that when we talk about a nonlinear molecule, nonlinear, we are going to have how many rotational degrees of freedom? All right, so I have a linear molecule. 2 angles describe its position in space. I add another dimension to that, third dimension. I need another degree of freedom to describe that. So how many degrees of freedom for rotations? 3. Thank you. All right, so 3. And therefore, the rotational energy, U rotational, will be 3/2 RT. Okay? All right, the next term is going to be the term due to the 0-point vibrational energy. And then we have the energy of vibration above that 0 point. And then this last one refers to the ground electronic state. All right? Now, if I take the derivative of this with respect to T, that gives me my heat capacity. All right? We notice that we have no temperature dependence on those 2 terms. So that means they're going to disappear. No T, no T. And therefore, the derivatives of those will go to 0. Okay? All right, and what we're left with is, and here I'm going to write this out explicitly a little bit. This is going to be 3/2 R. That will be CV for translation, plus R will be CV for rotation. And then the rest of it is CV vibration. I'm not going to rewrite the whole equation, right? But that refers to this. Okay? Does that make sense? All right, and then we can rewrite that reference to R, and that's what we end up with. All right? Section 7, we're going to talk about vibrational partition functions for polyatomics. So this will be Q vibration for polyatomics. Okay? All right. So, thinking back to chapter 1, we needed to talk about the number of vibrational modes, that is the number of ways that the molecule can vibrate. For a linear molecule, it's going to be 3n minus, and for nonlinear, it's going to be 3n minus, where n's the number of atoms in the molecule, right? And then just putting this in perspective, we know that this is the total number of degrees of freedom available to our molecule. How many do we use for translation? 3. And if it's linear, I use 2, so it's 3n minus 5. All right, and I'm going to say that's equal to alpha. All right, and then for nonlinear, we've established we still have 3 translational degrees of freedom. We now have 3 rotational degrees of freedom, and therefore it's 3n minus 6. All right, and that's going to be alpha. So alpha, whoops, that's a bad alpha. Number of vibrational modes. I'm so excited, I'm misspelling everything. All right, there we go. All right. Okay, and then we've also pointed out that when we have multiple vibrational modes, each of those modes can be treated as an independent harmonic oscillator. All right. And so if I think about the energies, I need to think about the energy for each of the vibrational modes that are available. All right. And for each one, that will be given by Planck's constant times the fundamental frequency of that mode, and then times our index, which will be the vibrational quantum number, plus 1/2. And V can have values 0, 1, 2, etc. Okay? All right. And then if I want to know the total vibrational energy of my molecule or my particle, what I need to do is sum those terms over all of the vibrational modes that I have. So that's going to be the summation of J equals 1 to alpha, because alpha is the number of vibrational modes that we have. It'll be H nu J, referring to each individual mode, and then whatever vibrational state I'm in, plus 1/2, right? So if I have a molecule that has 3 vibrational modes, I will have an energy associated with each of those, right? And I have 3 different harmonic oscillators with 3 different fundamental frequencies. And as we've seen multiple times, when we go to do partition functions for energies that are a summation, we know that we can look at the product of those, all right? So our overall vibrational partition function will be Q of vibration for mode 1 times Q of vibration for mode 2, all the way up to Q of vibration for mode alpha, okay? And again, if I have 3 energy terms that I need to think about, that means I'm going to have 3 different vibrational partition functions that I multiply by each other to give us the overall partition function for vibration, right? And this is where we pull in what we've previously derived. We know that the definition of our vibrational partition function is the summation of the Boltzmann factors. We have shown that that's the same as this analytic expression. We've simplified it by adding in vibrational temperatures, all right? And so what we can say then, if I want to talk about our overall vibrational partition function, that's going to be the product, all right? So that's our capital pi. We'll start with J equals 1, going up to alpha, and that will be e to the minus our vibrational temperature for that J vibrational mode divided by 1 minus, whoops, and I forgot something, 2 T, and then e to the minus our vibrational temperature reference to T. Okay? All right? Does that make sense? All right, and then we know once we have this partition function, we can take the partial of the natural log of Q with respect to T, multiply it by kBT squared, and that gets us our vibrational energy. Yeah?
Is that bottom theta 5 still in reference to J?
Yes, it is. Thank you. Yes, it is. Okay? Make sense? All right. And we've seen this, this before. This will be for each of our modes, the 0 point, and this is the energy above the 0 point. This is for one molecule, and then I multiply it by the number of particles that I have, and that gives me the energy of vibration for all the particles in my system, right? And this is just a simple rearrangement of that, okay? All right, let's take a moment to do a quick calculation and see if we can make some sense out of it. All right, so let's talk about the contribution to the vibrational heat capacity for water, all right? And I do want to point out that there's another example that's similar to this in the textbook. All right, so the first thing that we need to know is how many terms we're going to need for the heat capacity or for the energy, right? So that means we need to know the number of vibrational modes. So how many atoms do I have in water? 3 times 3, that's 9. Is water linear or nonlinear? It's nonlinear, so it's 3 times 3 minus 6, and that means that I'm going to have 3 vibrational modes. Okay? So if I were calculating the energy, that means I would have 3 terms. Whoops, 3 terms. Okay? All right, now because we're explicitly thinking about the heat capacity, we're going to talk about that separately. So we go to a table, right, and again, big picture. We can find a table that has vibrational temperatures for water. We know that comes from fundamental frequencies for water, which means these all come from vibrational spectroscopy. Okay? And those 3 values that are listed there are 5360 Kelvin, 5160 Kelvin, and 2290 Kelvin. Okay? All right, so my question for you is, for these each represent independent harmonic oscillators, right? Which one of these is going to have the lowest fundamental frequency? It's going to be a third one, right? Okay, because what we've seen is as the fundamental frequency goes up, our energy separation is greater, right? Okay? This is going to have the smallest fundamental frequency, and that also means it's going to have the smallest force constant. Okay? Does that make sense? So I'm just going to label this smallest frequency and K. Okay? All right. And then we, step back and say, this will be the highest fundamental frequency. This one will correspond to the largest force constant. And then I ask the question, if you were asked to bend this harmonic oscillator, get it moving, which mode is going to be the hardest one to do? It's going to be this one, right? So that's our stiffest harmonic oscillator. It's the stiffest spring. Okay? All right, now we know that what we're going to do is we're going to calculate 3 different contributions to heat capacity, one for this mode, and this mode. And we look at the overall calculation. We've got the vibrational temperature, reference to the temperature that we're interested in. We're looking at room temperature, so I've chosen to calculate 5360 over 300, 5160 over 300, 2290 over 300, right? So this gives me these 3 terms, right? So each of those will get plugged in to the separate entry for the heat capacity contribution. That's what we've got down here. I've just done a little bit of arithmetic and rearranged it so it's going to be referenced to R. All right. So once I have that equation, all I need to do is put in the vibrational temperature over the actual temperature of the room. All right. And when I do that, I see that I get 3 contributions. So this is going to be C vibe for 5360. This is going to be C vibe for 5160. And this last one is going to be C vibe for 22, and I've forgotten what it is now, 2290. Okay? All right. Okay, so let's take a look at this a little bit. So what does this tell us? One of the things that we see is if I said to you which mode, the stiffest mode or the weakest, the loosest mode, contributes greatest to the heat capacity. It's going to be the loosest, right? Okay, right? And so what we can say is that the larger the vibrational temperature, the lower the contribution, all right? So the lower C vibe of that mode. Okay? All right. And this is, this is explained. Basically what we're saying is if I have a really stiff spring, all right, I need to dump a lot of energy in it to get it moving, all right? So if I'm talking about low temperatures like room temperature, I'm not able to access that state as easily as I can access the lower energy states. Does that make sense? Okay. All right. So this shows graphically an example of that. So let's look. This is carbon dioxide. So for carbon dioxide, we've previously seen that, well, we know it's linear. There's 3 atoms, so it's 3n minus 5. There's 4 vibrational modes, right? 2 of the vibrational modes are exactly the same. If you think back to when we talked about CO2, that's going to be this mode and this mode, right? Those are the same energy, okay, associated with those. And then I've got 2 stretching modes, right? This shows the calculation of the contribution to the vibrational heat capacity as a function of temperature, all right? And so a couple things to note, right? If I choose some arbitrary temperature, what I see is that the lowest contribution is associated with the stiffest spring. And this is going to correspond, the maximum is going to be the loosest spring. Okay? All right, so practically speaking, what this is saying is if I have CO2 molecules in a box, I raise the temperature, what we see is that this gets excited at room temperature before this does. Okay? Our limits are the same. In the limit of low temperatures, we see that the contribution's going to 0. And in high temperatures, we see the limits going up to R, right? Okay, and we've shown multiple times that the high temperature limit is R, right? All right, so next up, we're going to talk about Q rotation for polyatomics. All right, so we'll start with linear, all right? And it turns out that for a linear molecule, our rotational partition function is exactly the same as what we've seen for a diatomic, right? So that's pretty easy, straightforward, okay? All right. And then way back in chapter 1, when we talked about rotations of nonlinear molecules, we didn't do any derivations, but we did mention that we have 3 independent moments of inertia, right? And so each of those independent moments of inertia is going to have a temperature associated with it, all right? And so the important thing for us is we have this rotational partition function that's got a t to the 3 halves dependence. So t to the 3 halves, and then times everything else has no temperature associated with it, okay? Right? And basically, we've shown this previously. If I'm talking about taking this partition function, I take the partial and natural log of q with respect to t, multiply it by kbt squared, and in this case, it's going to give me 3 halves RT. Okay? And that's, again, because we have 3 rotational degrees of freedom. Right? I take the derivative of this with respect to t, that gets my heat capacity, 3 halves R. Okay? All right. So next up, we're going to conclude this chapter by just summarizing sort of everything together, okay? All right, and so I'm going to go through it pretty quickly because we've seen it all before. This is just showing it at one. So I'm talking about an ideal gas. In all cases, we're talking about ideal gases. If it's linear, we've got our translational contribution to the to the partition function. We have our rotational and we have our vibrational, and we see the number of modes that are in there. That's new today. And then we need to worry about whatever the electronic energy is. All right, so that's there. And then I know that I can take the derivative of the natural log of Q with respect to T, multiply it by kBT squared. I end up with the energy. We can write it in this form or this form. This is mostly to be consistent with what the text presents. All right. I take the derivative of this with respect to T. That gets me my heat capacity. So my heat capacity, there's my translational contribution, my vibrational or my rotational contribution, my vibrational contribution. Because there's no temperature dependence here, all right, and there's no temperature dependence here, those guys disappear. Okay? All right. And in the homework number 8, I'm pretty sure it's next week's, basically what we're going to do is we're going to have you look at these heat capacities, say we're going to raise the temperature, where does the energy go? All right, so does it go into vibration, translation, or rotation? Okay, so it gives you a little bit of feel for the sense of that. Okay. All right, and then nonlinear ideal gas looks very similar. I've highlighted the differences in blue. All right, so what we've just seen is our rotational partition function is a little bit more complicated, but because we're interested in the temperature dependence, T to the 3/2 is what's key to that. The other place that we see a difference is the number of vibrational degrees of freedom. Right? Because we have different rotational degrees of freedom, we have a different total number of vibrational modes. Right? Okay. And again, we can take the derivative of the natural log of Q with respect to T, multiplied by kBT squared, and that gets the energy of the system, and take the derivative of that with respect to T, that gives me our contribution to the heat capacity. Right? So we have translation, rotation, vibration. Okay? Make sense? Okay. All right. I did want to close out by looking at this very quickly. So this is looking at water. All right. So this is the heat capacity reference to R. All right. This is what we would calculate assuming the ideal gas with the partition functions that we've introduced. Here's our experiment. All right. What we can see is that we're doing a good job at describing the experiment. All right. So that says what we're doing makes some sense. Now it does make a little bit of sense for us to stop to look at this a little bit more closely. One of the things that we see is as we're going to lower and lower temperatures, it looks like we're ending up at 3R. All right. And that's due to contributions from translation. That would be 3/2 R. Right, and rotation. And because water is a nonlinear molecule, we have 3/2 R contribution there. The sum of those two contributions is going to give me 3R. Thus, I go to 3 in the limit of low temperatures. Okay? All right. And then if I did this graph further, we would expect this to go up to a total of 6R. All right? Because for water, we know there are 3 vibrational modes, and each vibrational mode has a high temperature limit of R, right? From 3 modes. Okay? 6. Does that make sense? Okay? All right, I did want to take a moment to summarize something with an eye towards the future a little bit. All right, so for ideal gases, what we have shown is that U per mole will be equal to, I'm going to start with, how do I want to do this? We'll do it with a linear molecule. Right? It's going to be 3/2 RT, right? That's from translation. Because it is linear, its rotational contribution will be RT, right? And then I'm going to have the summation from J equals 1 to alpha. So I'm just generalizing here of my contribution from vibrations. So that's going to be e to the minus theta vibe over 2t over 1 minus e to the minus theta vibe over t. All right, and then I'm just going to generically say if there's an electronic contribution, it'll be u electronic. Okay? All right, so that's for a linear molecule. If I do it for a nonlinear molecule, the first term is identical. The vibrational, as I've described this, is identical because I'm going to the total number of modes. And my electronic, because I've generically indicated that, will just be the electronic energy. And where we see a difference is 3/2 RT. Okay? And then if I'm interested in a single atom, monoatomic ideal gas, it's simply going to be 3/2 RT plus the electronic. Okay? All right, so one of the things that we notice is that this is per mole, all right? And so if I have 2 moles, we would expect twice the energy, all right? So we clearly can say that the energy of our system, so here I'm going to be just generic, the energy is going to be a function of the number of moles or the number of particles, right? Because we know they're proportional to each other. The other thing that we see that's important in here is the temperature, right? Okay? One of the things that we see is that it is not a function of volume, right? All right, so, stepping back, think about this big picture. If I say that the energy of my ideal gas has changed, there's only 2 ways to change it. I change the temperature or I change the number of moles. Does that make sense? Okay? If I change the volume, doesn't do it. Okay? So what we can say is if n constant, then u is a function of t only. If delta t is equal to 0, what can you say about delta u then? It has to be equal to 0, okay? All right, that's a really important concept that we're going to be utilizing in Chapter 5, okay? Okay, next up, what we're going to be doing is talking about partial differentiation. How many people are familiar with that before? We've been doing it a little bit, but have you seen it in math? Does that show up in 265? Is that right? Okay. All right, so I want to just show a picture real quickly that describes what our goal is here, if I can find it. Okay? All right, so this shows a function that depends upon 2 variables, x and y. Does that make sense? Right? If I'm interested in looking at the impact of changing x on the function, I'm going to hold y constant, right? So that means I'm going to look at a slice of this with y equal to a constant. We good with that? And if I'm interested in the impact of changing x on the function, then I'm going to hold y constant, and I'm going to look at a slice in this direction. Does that make sense? Okay? So that's in the back. Keep that in the back of your mind, right? Then what I want to do is talk about how we use calculus to determine those relationships, all right? So I'm going to choose a slice. I'm going to look at f of x, function of x. I'm just drawing an arbitrary function on there, all right? And what we're interested in is knowing the impact of changing the function, or the impact on the function that's caused by changing variable x. Necessarily, I'm going to be holding y constant, right? So what we know that we can do is that we can look at the slope, right? So I'm just going to draw an arbitrary slope in there, right? And that slope is going to be df dx, right? So I'm going to write in df dx. I'm going to hold y constant and all the other variables that may be important. Now if I want, so this tells me how the function responds to a small change in x, right? Infinitesimal change in x, that creates an infinitesimal change in f. Now if I want only the change in f, what do I need to multiply this by? This is df, I want df, so I need to multiply this by dx, right? That's important, okay? Okay? We got that? Right. And then what we can say is that, well, if I'm interested in looking at the change in my function due to a change in y, then I'm going to hold x constant, and I'm going to do the same thing, right? So I don't want to draw another graph, but we can look at the other axis, right, and say that df is equal to df dy. We need to hold x constant and then dy, right? And then if I want to generalize and say, what if I change both x and y, right? Then what I can do is I can say df is equal to this term plus this term. And that will give me the dependence upon changes in x and y independent of each other. Does that make sense to everybody? All right, that's where we're going to pick up next time. I'm letting you out a little early. For whatever reason, at 1 o'clock, I always get behind. All right, have a good one. We'll see you guys on Friday.